one of the lecture series that we need to tackle for the next part, which is the electricity cost and delivery. This is a part of the course EE184 or Power System Supply. Okay, to begin with, we have the introduction in terms of the electricity utilities in the US, which has a total of 3,130 terawatt hour. So when you say 3130 terawatt hour, terawatt means times 10 to the 12 of electrical energy usage to any of the three types of customers. Actually, the three types of customers is an industrial, commercial, and residential. It's like lower voltage, medium voltage, and high voltage respectively. Then, this is the table or W of all of the types of customers with the number of customers itself, as well as the total consumption in terms of terawatt hour. So as you can see here, it's very clear that the residential customers has plenty, which constitute almost 80% of a total population, then followed by a commercial customer, which is the medium range, and industrial, which is composed of almost 5 to 10%. In terms of the total amount of consumption, it is clear also that the industrial customers has plenty of amount of energy in terms of 1080 terawatt hours, and the monthly consumption also has a higher value in terms of its corresponding kilowatt hour rate. But the enormous amount of electricity will always represent a 1.1 kilowatt hour of power, which is continuous in every 24 hours a day, every woman and child. Now the question is, this 1.1 kilowatts, which can be computed from the table. So we will go back to the table, and then from the table, as you can see, we can have the rate, in terms of the corresponding power. If we have 1,141 terawatt hour, which is times 10 to the 12, if I divide it by the number of customers, 109,817,000, we can have an approximate of 10.39 megawatt hour per customer. So, if we have the total periodic hour in terms of yearly basis, we have 8,760 hours per year. The hours will cancel, and therefore, we can have at least an approximate of 1.186 megawatt per yearly basis. So this is an approximate of 1.1. So since we have residential customers, which is 80% of the total population, it's clear that when you use the energy in terms of 24/7 basis, you can have at least 1.1 megawatt hour. So this is the main reason why we have that enormous amount of at least 1.1 kilowatts in terms of 24/7. And therefore, the question is, how much energy that will cost? So you have here two categories in terms of costing. So fixed as well as the operating cost. Now the question is, what is operating and what is fixed? So fixed cost means the depreciation charges from building dams and turbines. So this is the so-called permanent cost for this type of structures. Then when I say operating costs, it includes salaries, fuel costs, admin positions, and other daily expenses, which is clear that we have water, we have telephones, we have electricity bills. So if you add up fixed costs and electricity costs, that's the total cost. Okay, in every country, we have some rate guidelines. And the rate guidelines is dependent upon three important things. The first is the amount of energy or the rate of energy per kilowatt hour, the maximum demand, as well as the power factor of the load. In the next few slides, we can discuss these three in detail. Okay, first, we need to know the tariff based on energy. As we can see here, electricity can be computed in terms of rate if we divide the total energy by the corresponding time, or the so-called the area under the curve. Now, in the US, as an example, domestic tariff will start from 20 cents per kilowatt at the first 100 kilowatt, and falls down to 10 cents, 200 kilowatt, and then 8 cents. It's like when you buy a certain commodity in terms of retail. If you have retail, the larger the cost. If you have, of course, more commodities that you will use or wholesale, it will give a lesser cost. It's like energy, because energy is like energy trading. The more energy that you consume, the lesser the cost. Okay, let's have an example here in terms of maximum demand. In terms of the maximum demand, it's very clear that we have the electricity cost that is based on that. And the electricity cost is based on the maximum demand in terms of time interval. The time interval will definitely depends on 1 day, 30 days, or even 1 year. In terms of hours, it is clear that we have 24 hours, we have 720, and you have 8760 hours in terms of hourly basis or hour basis. Okay, as an example, we can have the tariff in terms of maximum demand. Maximum demand curves is depend upon the largest point, where in terms of a certain time interval, you can have that as your maximum demand. Now, we have here two factories A and B that we can, of course, compare. Okay, first of which is you have a factory A, and it has here your energy consumption. You have your factory B, and it has this a monthly load curve. Okay, as you can see here, the rate of consumption is constant, simply because, if you can see here, you can compute for the energy output by multiplying the output power multiplied by a certain time interval. So, it is also clear that the area under the curve is our energy output. Now, if you have 1,000 kilowatts here, and that is your width, you have here you form here a rectangle. So the area of a rectangle is simply length times width. Now the length here is very clear that you have 30 days, or simply 720 hours. If you compute 720 hours with the maximum demand, you can have here at least 720,000 kilowatt hours of energy. So in this case, yes, the rate, it depends on the maximum demand. While in the second curve, as you can see, or second factory, the curve is intermittent. When you say intermittent, you do not know, here, based on the curve, if that is EO is equal to P out times time. Now, again, you cannot establish here in a point where if you get EO, then multiply by time, and then what you will do is to add it up, or to get the average. Now, this is different. Okay? You need to use a numerical integration here to get the total energy developed, or the so-called 1/3 Simpson rule. So 1/3 Simpson rule is very important in terms of getting the total energy produced in an intermittent source. Okay, for that one, since we do not establish a perfect rectangular curve, if you use numerical integration, they have the same energy output based from the calculation. But the difference is, as you can see, the maximum demand occurs at 3,000 kilowatt. So it means that the maximum demand here is 3,000 kilowatts, and hence 3,000 kilowatts is obviously greater than 1,000 kilowatt, and it's very evident that some of the auxiliaries of the system will have twice of the consumption, or rather twice of the size. From the equation itself, of a very simple equation, VI conjugate, okay? The apparent power is proportional to the current. Now, considering our max demand here in terms of kilowatt, okay? We can see the larger the output or maximum demand, the greater the current. The greater the current means greater size of the conductor, greater auxiliary ratings, therefore higher cost. So that's the main difference between the tariff of a certain factory with a constant rate rather than a factory having intermittent maximum or intermittent rates or intermittent. Okay, since we established that comparison, hence we can now say that the figures from the last, last factory or the last factory means there are many power spikes or intermittency, and thus it corresponds high power drawn because of inrush currents. Hence, the question is, how can we say that the power surge have lasted or meaning it considers significant? Okay, the answer here is depends on the time interval. Okay, when I say a time interval, in terms of minutes, hours, or seconds. Okay, if we establish 5 minutes, then it depends on the loading. 15 minutes, 30 minutes, or even a 60 minutes or 1 hour interval. Okay, this is the time interval that you need to know for the so-called maximum demand. Okay, a maximum demand needs a meter wherein we can measure the kilowatt demand in every time interval. Okay, a demand meter is a meter that is installed at customer service. So it actually measures average power during time interval, which is called the demand. Okay, here we have 2 pointers, which is very important on a maximum in a demand meter. Okay, first pointer, okay, it measures the average power. Religiously, it measures the average power. The second pointer is it measures the maximum demand. And that is a demand meter. So since the demand meter that we will tackle today is an electromechanical device, so it means it is not digital. So it depends on the pointer wherein it has an analog reading. An example of a demand meter is like this. So it's like a kilowatt hour relay, okay, that can measure the maximum demand, or even an analog device that can also print the maximum demand if it is necessary or if it is needed for certain application. Okay, to understand further, what I'm trying to say here is we have an example in terms of graph. So in terms of low duration graphs, in terms of bar graph. A certain graph has an active power drawn from a large factory from 7 to 9 in the morning. And the meter assumes that the pointer, first pointer rather, is 2 megawatt. While the second has an indication of 3 megawatt. Now the question is, what will be the readings at the following times from 7:30, 8, 8:30, and 9? Okay, our salient points here is at 7 a.m., At 7 a.m., you have a 2 megawatt reading. And then your maximum demand reading is 3 megawatt. So this is the first pointer and the second pointer, and this is the time. The time is 7 a.m. Okay. We can establish that using the bar curve, as I mentioned a while ago, the low duration curve. So this is the curve from 7 a.m. to 9. And you need to establish the readings based on the bar curve. The y-axis is your megawatts, while your x-axis is the time in terms of interval minutes of 15 minutes per interval. Okay, to understand it further, we can have here, okay, the solution. According to the graph, we can have the first interval here of 7 to 7:30. We establish a 2 megawatt here simply because it is a constant. So, if that is a constant, the answer is 2 megawatt. Now, if that is 2 megawatt, that is for pointer 1. It measures the average power. Now, the second pointer still at the 3 megawatt side. In 7 a.m., okay, 2 megawatt, then 3 megawatt. Now, this is the first pointer and this is the second pointer. Now, at 7:30, okay, is established at 2 megawatts. Now, since the 2 megawatt here did not beat the 3 megawatts, the second pointer, which is our maximum demand pointer, still at 3 megawatts. Okay, now, from 7:30 now to 8. At 8 o'clock, what will be the readings? So, we will establish at 60. Now, since we already know that E out is P out times time, or P out is E out divided by time, the area under the curve will be your EO. So, if you multiply this interval here by the corresponding power, we can now get the so-called EO. But to get PO, we need to divide it by the interval. Since we have 30 minutes, we can multiply 7 by 5 minutes, which is this, at 5-minute interval. Then another 5 minutes, that is for 2. And then plus 4 times how many minutes? That is 20. Since we're dealing with 30 minutes for 7:30 to 8, that it will be stopped here at 60. Hence, if we divide it by 30, the answer is 4.70. So it means, at the end of the average hour, we have 4.17. Now, for this, okay, 4.70 megawatt, since the 4.70 beats the 3 megawatt pointer, or the maximum demand, the maximum demand will become 4.70 now. Because the first pointer religiously gets the average power based on a certain curve. But the second pointer will be dependent upon what will be the reading at a certain time interval, then that will be your maximum. Okay, let's move forward to letter C. At letter C, we have 8:30 a.m. Okay, from 8:30 a.m., which is up to 90, we do the same pattern. Okay, we multiply 7 by 5 minutes, 8 by 5 minutes, 4 by 5 minutes, and etc. Then divide it by 30. This is the curve from 60 to 90, and you divide it by the time interval. The answer will become 4.67. So from 4.67 megawatt, since it beats the 4.17 maximum demand previously, so hence, we can have 4.67 megawatts at the end of the maximum demand. Last but not the least, if you want to have the 90 up to 120 here, which is 9 o'clock, okay, do the same pattern. Multiply 1 by 5, 12 by 5 from the curve, and then 1 times 20 is divided by 30. The answer is 2.83. Now, from 2.83 megawatts, since 2.83 megawatts did not beat the previous maximum demand reading, hence our maximum reading will be at 4.67. So again, this is the time, the importance in terms of time interval, and the maximum demand, which is very important also on the rate guidelines. And one of them, of the equipment that is used here, is the so-called